which was does the time average of a system and the space average of a system agree? They had a feeling that the space average of the temperature would also be the time average of the temperature. And Boltzmann felt that if orbits penetrated all possible states of the space, then it would follow that the equilibrium value of physical quantity would coincide with its weighted average value over all states. Maybe that's a clearer way of saying it. And that was the sort of ergodic hypothesis. So this is the second hypothesis, is recurrence. It's the qualitative behavior of orbits. So do orbits come back always to the same set of positive measure? Is it visited often? So if space averages and time averages agree, it's called an ergodic system. So ergos means work in Greek, and ergodic means the study of work, and it's this thermodynamical work that gives the subject its name. In fact, this happens is equivalent to saying, or orbits visit every set of positive measure infinitely often, as we'll see. Let me write that in symbols. So if I wanted to write in terms of measure theory what that meant, this is what I would write. There are some other recurrence properties. Are called strong mixing. Which is the limit as n goes to infinity of mu of t to the n e intersection f equals mu e mu f, for example. And then there's also something called weak mixing, which is somewhere between ergodicity and strong mixing, which I'll talk about later. And there's recurrence itself. Which says that mu of e intersection t to the ne And actually this holds in any set of any probability space. So there is a bunch of, so that's the first questions are around the convergence of these averages. The second questions are around recurrence properties, which are properties of orbits. The third major question, which is a classification problem. So it's called metric isomorphism. Unfortunately, this has got nothing to do with metric spaces. Metric means measurement, and it's the mu and the nu that are measuring things. So it's a historical confusion of terms. Probably if we were doing things again, we wouldn't call it metric isomorphism, but that's the name that everybody calls it in this subject. If there exist sets x naught, y naught of measure 0, and bijective map, bimeasurable map, say phi from x onto y. Oh no, x take away x naught, onto y take away y naught. One has to be careful sometimes about sets of measure 0 in this subject. So that phi t equals s phi, so it intertwines, if you like. In harmonic analysis, we would certainly call this intertwining, the two transformations s and t. And I always get this the wrong way around. Mu of phi minus 1e equals nu of e for all e in C. So that's a natural way of all the states of the system X correspond to one-to-one to states of the system Y, and everything is preserved. The dynamics is preserved and the measure is preserved. Sometimes it's called an isomorphism. Modulo 0 because of these sets of measure 0. So this question is, how can you tell? And so the classical way has been doing to this. Is to attach some invariant to the system which is invariant under this transformation, e.g. recurrence, e.g. ergodicity, recurrence, mixing, etc. Yes? Yes, perhaps I'm writing smaller and smaller. I'll try and write larger and larger. Thank you for reminding me. And my handwriting is worse too. Attach invariants to them. And then I said e.g. ergodicity, recurrence, or mixing. So those are invariance properties which are preserved under this metric isomorphism thing. There are also things called spectral invariance. Which I'm going to talk about later in today's talk, but I mean basically Yes. Oh, I see. But it doesn't matter. No, I'm not assuming that, but it doesn't matter. T is actually generally only defined up to sets of measure 0 anyway. AE. Good, I'm glad the audience is awake. Thank you. So you can compose an L2 function with T like this, and then you can think of T as becoming an operator on L2, and the spectrum of that operator is an interesting invariant. And so that's called the Koopman operator then, and I'll be discussing that a little bit. A more recent one is sorry? Bigger letters. So entropy is something that I'll certainly be discussing later on as well. And a coarser type of in orbit equivalence, we don't assume this, but we just assume that phi maps the orbits of S, orbits of T to orbits of S. And that's a topic I'll be discussing later in the thing. So here are two other questions. So the realization problem is, suppose we understand equivalence classes here. What's a good model for what the systems look like? And what is a typical system like, and how can you realize them properly? So for me, I think those questions summarize what ergodic theory is about. It's trying to answer those questions. I hope you'll forgive me for talking in sort of generalities like this, but I think it's important to see the shape of the subject as we go into it. So now, having said that, let me tell you what I'm going to do in my lectures. So my first, I think it might take me a little longer than just today. which is largely about measure-preserving actions of Z. And I hope to start some extensions to amenable groups. My second lecture, I'm planning to talk about entropy. My third one, I'm going to talk about non-singular. And orbit equivalence. This is kind of related to von Neumann algebras a little bit too, and then my last lecture is going to be about non-amenable group actions. So that's the plan of what I'm aiming to do. Is that clear? Does anybody want me to do other topics that are not included? Okay, I've spent quite a lot of time on this beginning, but I think it's important to set the whole subject in context because I realize it's new for many of you. And so I've written quite a lot of notes, but I've done it all handwritten in a very old-fashioned session. I noticed when I was a young boy, people always used to write on the blackboard, and then after a time, all mathematicians started using PowerPoint. And now I've noticed that the younger mathematicians are starting to write on the blackboard again, whereas the older mathematicians are using PowerPoint. So I'm attempting to return to the past and do this course. So I've written notes like this on pencil and paper, and I'm writing up on the blackboard. However, what I'm going to offer is that I'll make available a photocopy of these notes, which we'll then put up on the web, and you can all have a look at them. So there are some more details sometimes, and perhaps my handwriting is epsilon better here than it is on the blackboard. So the first theorem is the von Neumann ergodic theorem. That's where the subject started, so I thought it was a good place to start. I'd like to tell you about 4 ergodic theorems, actually. So if H is a Hilbert space, this is a slightly T, a contraction of H. For all n, then for all H in H, A n H converges to P1H. where what is P1H which is the kernel of T minus the identity of T invariant vectors. So what that means is that the limit of this is